everyone. Alright, let's go ahead and let's get started. So you had on page 134 to 135 questions 6 through 10. So let's go over those first. What term refers to a category of elements characterized as being hard, dense, and shiny, and good electrical conductors? So it's asking like the ideas of metals, semi-metals, or non-metals. So hopefully you wrote metals as the answer for it. Number 7, what group contains the alkali metals, and which element in this group is not an alkali metal? That is group 1, and it's hydrogen, specifically that it is not a metal, and we'll talk about the reasons why. Number 8, what elements fit between group 3 and 4 of the periodic table? That is the inner transition metals. Number 9, what is the name for the group given to the elements in group 17 of the periodic table, such as fluorine and chlorine? We call those halogens. We'll talk about the reasons why later. Number 10, which term refers to elements that do not combine readily with other elements because they already have 8 electrons in their valence shell? Those are the noble gases, and we'll talk more about them later. Alright, so I emailed your parents telling you that you have a quiz today. I emailed them this morning, so they might not have it ready for you, so I'm sorry for the late notice for it. But let's go ahead and let's study and let's review for it. So for your classwork, it's pages 113 through 120. Try to see how many bold terms and definitions you can write down in about 5 to 10 minutes. So we've been reviewing over this for several days now. You don't have to worry about the periodic table today, but make sure that you are studying the bold terms and the definitions. So go back to page 113. Sorry, I started early. So page 113 to 122. Go back and write down as many bold terms and definitions, as many as you can in about 5 to 10 minutes. If you want to pause the video and go ask your parents or your proctor or whoever's doing this with you for the quiz, don't look at it yet. But if you want to go ask them for it, you can, but don't look at it yet. No cheating. Alright, so go ahead and pause the video and work on your classwork. Alright, assuming that you're still with me, then that means you already finished your classwork, so let's go over it. So I'm going to go over the italicized words as well. So hopefully as you were going through them, trying to study and hopefully cram them in as much as you can, hopefully you realize, okay, I know most of this already. I want to go over the important italicized words and phrases as well. Alright, so what is the organized study of composition and interactions of matter? That is chemistry. Alright, who came up with the atomic theory of matter? John Dalton. There are 5 parts to his atomic theory. What are they? Do you know? Can you say them without looking? Remember, there's the 5 parts. That every element consists of tiny particles called atoms. All atoms of a particular element have the same properties. Different elements have different properties because their atoms are different, and atoms of different elements can combine in a specific way to form compounds. And chemical processes are the result of rearrangement, recombination, or separation of atoms. Alright, so just bringing out that John Dalton thought that all matter was made up of indestructible little particles called atoms. We know today that you can split an atom, but he thought that it would basically be like hard spheres, and that's why he called them atoms. Now, what do you call a substance that's made up of one type of atom? So we have a periodic table that has all these listed, but what do you call they're composed of one type of atom? An element. What do you call just 2 or more atoms hooked up together? Could be the same, could be different. Just 2 or more hooked up together. It's a molecule. What if it's 2 or more different atoms specifically? That is a compound. Let's see. What do you call the unique abbreviation that is given to each element? So, like iron is given Fe. What do we call this? You had to memorize all these. Chemical symbols. Good job. So a chemical symbol is the unique abbreviation given to the elements. Let's see. What do we call the smaller particles that make up an atom? So they're smaller than an atom. This is what an atom can be broken apart into. There's 3 of them. Subatomic particles. So going through this, what is the name for the 2 particles in the nucleus? What's the name for both of them? Nucleons. So make a note, nucleons. These are subatomic particles found in the nucleus of an atom. So what are they? What particles make up the nucleus? Protons and neutrons. Good job. Protons have a what type of charge? Or none? Right, they have a positive 1 charge. Neutrons have what type of charge? Or none? Right, neutrons are neutral, so they have no charge, so there is nothing there. So sometimes we'll draw it as kind of, well, no, we draw it typically as 0, the idea of no charge. Now remember, our electrons on the inside of the nucleus of the atom. Nope, they are flying around it. So electrons, they have, let's see, they're not parts of the nucleus, but they are attracted to it. What charge do the electrons have? Right, they have a charge of -1. So they balance out the protons. Alright, what determines the identity of the element? Protons, neutrons, or electrons? Protons. What do we call the number of protons? It's the what? Atomic number. Good job. All right, what do you call an element that has a different number of neutrons? Could be heavier, could be lighter. Is how a lot of cases we refer to it as. An isotope. Good job. So they have the same number of protons, but different number of neutrons. All right, what do we think makes up protons and neutrons? Quarks. Good job. So they think it's the quarks that make up the protons and the neutrons. Oh, let's see. What do we think? No, we're not gonna ask that. All right, so let's see. I already asked that. All right, what do we call the layers that can hold electrons? What do we call those layers? So that the electrons are flying around in. Electron shells or energy layer. Sorry, I think I have chalk in my eye. Keeps blurring up. Sorry. Okay, so can you have a different number of electrons though? Yes. So typically, if you were to have a substance like carbon, since carbon's been my example for days now, carbon has 6 protons. So if you're going to have a neutral substance where it doesn't have any charge, how many electrons do I need? So if I have 6 protons, I have a positive plus charge. How many electrons do I need to get 0 or no charge? If each electron is -1. Right, I need 6 electrons. So that way it's positive 6 plus negative 6 equals 0. Sorry, I started early. Alright, so that's the idea of a neutral substance. Let's say though I have an extra electron. Will my overall charge be positive or negative? Right, it'll be, nope, not positive, almost a positive 1, -1. What do we call a substance that has a charge, either positive or negative? An ion. What if it has a negative charge specifically? That is an anion. What if it has a positive charge? Like for example, it has less electrons, so it has a positive charge. That is a cation. Good job. Now remember, can I change the number of protons if I want a positive charge? No, because I won't have carbon anymore. I'll have a whole different other element. So make a note for that. Alright, so what do we call the number? So if I were to write it like this at the top. So remember, this is the atomic number. What is the number that's written in the top that tells me the number of protons and neutrons together? Mass number. So for this example, this is carbon, well, carbon 14, but it has 8 neutrons in it. All right, how do we measure the mass of the atom? What unit do we use? Because we can't use grams because it's too small. AMUs, or atomic mass units. So sometimes your book gives it to you in U. AMU is another sign for it, or atomic mass units, making sure that you know all 3 for it. That's the unit we use to measure the weight of an atom. Alright, like for example, if you look at the periodic table for carbon, you'll notice it has the number 12.01. This represents the weight for the carbon element. Now, what do we call this? How did they decide on this as the weight? Right, it's the average atomic weight, or the average atomic mass. And so they said, okay, out of all the isotopes of carbon and how much of each isotope we found, this is the average atomic mass. So make a note of that bottom number underneath the element, that is the average atomic mass. It doesn't mean every single carbon weighs this, but this is the average atomic mass for the based on their isotopes and how many of each isotope we find. Alright, so what theory states that tiny particles such as electrons do not absorb or release energy in a smooth flow? They have to absorb it in these packets of quanta or quantum. That is the quantum theory. Who came up with the quantum theory? Max Planck, so make a note for him. Alright, who said that the electrons are locked into these orbits? To draw my nucleus again. He was saying, okay, sorry carbon, almost ran through you. So he's saying, okay, let's say now that the electrons, they're locked into these orbits, these circles basically, saying that they can't jump from one orbit to another one unless they lose or gain energy. Whose model is this? That's the Bohr model. It was invented by Niels Bohr. So it was come up with by Niels Bohr. So take a note for him. Alright, who came up with the wave mechanical model, saying that the electrons move not in these circles, but it's in this wave pattern as they go around it? Who came up with that idea? So that was Schrodinger. So make a note for him. Erwin Schrodinger. Make a note for him for it. Alright, who said you can't measure, okay, first of all, what is the principle that says you can't measure the position and the velocity of the electron at the exact same time. You either know where it's at, so that way you stop it, or you can measure its speed, but you don't know where it's at. So, what is that idea called, or what's that principle? Alright, your book gives it to you as Heisenberg uncertainty principle. If you just say uncertainty principle, because that's how the chemistry book gives it next year, that's fine too as well. But who came up with that idea? So, Werner Heisenberg, so make a note for him. Alright, who combined the Bohr model and the wave mechanical model and the Heisenberg uncertainty principle, saying that, okay, they're not in these orbits, they're in these regions of space. Which, first of all, what do we call these regions where you're going to find the electrons? Where it's not like the idea of a straight line, it's just these general regions where you have a high probability of finding them. What do we call those? It's not orbits. It's orbitals. Good job. So electrons move in unpredictable regions called orbitals. What do we call that model that uses orbitals? Right, it's the electron cloud model with the idea of they're all around it, but we're not sure exactly where they're at in regards to a straight line. Who came up with that model? Max Born. So Max Born came up with the electron cloud model, and you have orbitals in the electron cloud model, not orbits. Alright, so what do we use to mathematically represent the overall motion of each electron, or the overall position of each electron? What do we use to say, here's basically the address of the electron? Right, it's the 4 quantum numbers. The first quantum number tells you the electron shell or energy level. Second one tells you the shape. Third one tells you the orientation in space. And the first one describes you the spin. Alright, what principle says that no two electrons in an atom can have the same set 4 quantum numbers? The Pauli exclusion principle. Make a note for that, Pauli exclusion principle. Alright, so going on from it, what do we call a nucleus that is unstable? Radioactive. And so what do we call a process whenever you have the atomic nucleus breaks up or changes emitting radiation? Radioactive decay. There's 3 different types of radioactive decay. What's the first one that kicks off 2 protons and 2 neutrons? That's an alpha decay, and we call that the alpha particle. What's the symbol that's used for alpha decay? Right, it's the fish-looking thing. I'm going to roll it over here. So remember, it kicks off 2 protons and 2 neutrons. So that's basically a helium atom. Alright, oh, I almost skipped. What is the length of time it takes for 1/2 of a substance to decay into the new substance? What do we call that length of time whenever we're saying a radioactive substance is decaying from its old substance into a new one? That is the half-life. Good job. So it kind of makes sense for the name. Alright, what type of decay is it whenever you have in the nucleus the neutron changes into a proton and it kicks off an electron to balance out the charge? I'm going to use nitrogen as the example, even though nitrogen is stable and nitrogen doesn't do this. So you have nitrogen to where it changes into, let's say it's this. It changes into oxygen and it kicks off an electron to balance out the charge. Now keep in mind, does the mass number change? No, because you still have the same number of protons and neutrons. Now, you have 1 more proton, that's why the atomic number goes up, but the mass number doesn't change. So you have 1 element changing into another. What type of decay is that? That's beta decay. Good job. What's the symbol for beta decay? Right, it's the B with the extra tail. So make a note for that. So beta decay, the B with the extra little tail on it. What do you call the type of radiation that's extremely high wavelengths of energy and frequency? Gamma radiation. What's the symbol for gamma radiation? It looks like a Y, a little bit of a funkier Y, so make a note for that one. Now, let's see, can you absorb a little bit of radiation, or do you instantly die whenever you get radiation? Right, you can absorb a little bit of it. Now, too much of it is like a sunburn. Too much, and your body can't handle it. If you get a little bit, you're fine. That's good, because the earth is radioactive. You naturally get radiation from the earth, from the sun, from other people around you. You're going to naturally get radiation. Alright, what do you call it whenever you have 1 nucleus, it splits into 2 smaller nucleuses, or nuclei technically, and it becomes more stable? Is that fusion or fission? Fission. Good job. Alright, what do you call it whenever you have 1 nucleus, it splits, it kicks off its neutrons, and then they spread into other unstable isotopes, and then they start to split apart? So what do we call that when you have it to where it just keeps going and going and going? Chain reaction. Good job. It's kind of hard to describe. What do you call it whenever you have to have that certain amount of fissionable material present? Otherwise, you can't have a chaining reaction. So, like for uranium-235, you have to have 16 kilograms of it. Right, that's the critical mass. So the idea of you have to have this amount for it. If you don't have this amount, you're not going to have your chain reaction. All right, what do you call a device that initiates an uncontrolled chain reaction? An atomic bomb. So yes, atomic bomb is the answer for that one. What do you call a type of chain reaction that is harnessed by a device and uses it to produce energy? A nuclear reactor. Good job. What type of reactor is it whenever it uses more nuclear fuel than it spends? So it produces more nuclear fuel than it needs. We'll word it that way. That's a breeder reactor specifically. Alright, what was the horrible accident in Ukraine that was caused by the Soviet Union scientists basically being foolish? So Chernobyl, make a note for that. Alright, what do you call it whenever you have two smaller nucleuses that combine together to make a larger nucleus and they release a lot of energy? This is nuclear fusion. Alright, what's the type of bomb that uses nuclear fusion? You've never dropped this on anyone. The hydrogen bomb. So make a note for that. Alright, I believe that is everything. Let's see, making sure I covered everything for you. What are substances composed of a single type of atom? Pretty sure I asked this, just want to make sure. Like on the periodic table. What do you call a substance that's composed of one type of atom? Element, just want to make sure. Let's see. Yep, I believe that is everything. So, just make a note of it. So, if you want to take a minute to study really quick, go over these pages again for it, or to go over something in the review, you can. But go ahead and pause the video and work on that. Don't come back. Well, don't come back until you've taken your quiz, or don't come back until you've went and asked your proctor for it. So, your proctor should have it. So, remember, for this quiz, you only need the quiz and a pen. You don't need your calculator this time around because we don't have any math quite yet in this section. But just make sure you do have the working pen and the quiz. So you can put your cell phone away, your textbook away, everything off your desk so you have enough room to be able to work and be able to focus. So go ahead, put everything away, go ask your proctor for the quiz, and then go ahead and take it. Be sure to read carefully for your quiz. So don't watch the rest of the video though until you're ready to take it and until you've taken it. So go ahead and pause the video and go ask your proctor for it. Alright, assuming that you're back now, that means you finished taking your quiz for it. So, should have erased this as well for it. So hopefully you didn't look at the screen whenever you were taking your quiz as well, but you didn't need anything else besides just that pen and the quiz. So, let's go ahead and let's get into it though, talking about our section with the periodic table. So now we're getting into, on page number 130, getting into the electrons and chemical properties. Okay. So, in this section, we talked about the periodic table. We introduced this yesterday, but then we kind of ran out of time. So, getting into it, the several trends of the periodic table that make it a useful tool for scientists. So, getting into this section, that your book points out that the octet rule is one of the major reasons as to how come you can have elements combined with other elements. Now, we've been talking about nuclear chemistry, having changes in the nucleus of the atom. But most of your chemical reactions don't take place in the nucleus. Most of the cases it's with them gaining or losing electrons. Now remember, can you lose or gain electrons? Yes, you can, because you can have those ions. You're having them lose or gain them. Now, your book points out that the outermost shell is the valence shell. In a lot of cases, the most important layer of the atom. Most atoms tend to react that they want to have 8 electrons in that valence shell. They are happy or satisfied at that point. Some of them can hold way more electrons overall, but just that outermost shell, they want to have 8 in that one. Or they want to have nothing in it, or 8. That's pretty much how most of them react for it. Make a note, the electrons in that valence shell are known as valence electrons, so make a note for them because they're really important. And that's how a lot of atoms will chemically react for it. So, make a note of the octet rule, that most atoms tend to react to obtain 8 valence electrons in their valence shell. They either want 8 electrons there or none at all. So it's an all or nothing idea. Typically they don't want 9 or 10 or 5 or 6. They want 8, and that is it. So they want 8 there, or they don't want any of them in that outermost shell for it. Your book points out that not every element follows this rule. In particular, hydrogen and helium, because they're so small, they only need 2 valence electrons, and they're typically happy and satisfied at that point. but most of the other elements that they want those 8 valence electrons. Alright, periodic table. Now the periodic table was a man-made tool that scientists came up with to try to help show and to help use it with our chemical reactions. So the periodic table is a very handy tool, and there's a lot of things we can use the periodic table for. Alright, the periodic law states that when the elements are arranged by their increasing atomic numbers, they show regular or repeating or periodic properties. So the idea of you see these patterns over and over again in the periodic table. Now you'll notice that they increase by their atomic number. I've already pointed this out previously, but you'll notice if you want to look on your book, page 131 as well, if it's not showing up super well on your screen, that hydrogen has an atomic number of 1, and going across, helium has 2, going back down into the next layer, you have lithium has 3, beryllium has 4, going across, boron has 5, and so it's the idea of it's going across and down on the periodic table. And whenever you put them in that order, it shows regular, repeating, or periodic properties. Alright, so your book points out a table of elements arranged by atomic number and the number of valence electrons, with the idea there is a reason as to how come they have them spaced out like this. You might wonder, why is hydrogen over here, and why is helium way over here? Why didn't they just stick helium right here and just be done with it? There is a reason why for it. It has to do with their valence shell or their outermost electrons. So that's why it's 1, 2, 3, 4, 5, 6, way over there. And that's the reasons why for it. So scientists put them in order of atomic number, but then they also space them out with their valence electrons. So that's the reason why some, they look like that there's gaps or there's like weird spacing. That's the reason why for it. We call this arrangement the periodic table of elements. Make a note for that. So a table of elements arranged by atomic number and the number of valence electrons is the periodic table of elements. This particular version was organized by Dmitry Mendeleev. So just make a note for him that he came up with this particular arrangement, and we still use it today. So he came up with the best tool version of this. Alright, so the book starts talking about the different terms to note for it. So here's some terms to note for it. That if you have an up or down section, the column is a group. So remember, a column is kind of like the column of a building. So you might know columns like of architecture, how these help hold up the roofs of a building. So this is the upper or the roof or the ceiling of a building. Sometimes you'll see these on really old mansions, how they have those columns or pillars with the up and down part. We call those the groups. So make a note for that. So looking at the periodic table, you would have this be group 1, group 2, group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. In some cases, you have an older system. I believe your book shows you this as well, that you'll notice that it has 1A, 2A, 3B, 4B, 5B, and then it keeps going across, and then it jumps back over to 3A. That's the way I learned it when I was in high school. So just to let you know, your book points out as an older system. Occasionally, I might slip up and say 3A instead of 13. So just make a note though that if I say 3A, I'm referring to group 13. I try really hard to remember that occasionally it still slips out. So just make a note for it. It's just telling you that's the old system for it. Now, you might be wondering, why did they give them A's and B's then? Well, that's because some of them we work more with, and they're considered more important, or we consider the main group elements. So that's why they gave groups 1, 2, and then 3, well, 13, with the idea of 3A, 4A, 5A. That the A groups, those were considered the main group elements, or the representative elements. The main group elements are the representative elements. That's how come I learned them as 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, because those were the main groups. And then the B ones were the interposition metals, were the not as important ones. Now, since then they've swapped over and they said, okay, we're not going to do it like that anymore. We're going to do it to where it's just 1 through 18 and just make it easier. So that's the reason why though for it. So make a note that groups 1, 2, and 13 through 18, those are considered the main group elements or representative elements. Now, they're considered main group because there are these regular repeating patterns for them. Group 1 always has 1 valence electron. Remember, a valence electron is that outermost layer. So they have 1 outermost electron. Group 2 has 2 outermost electrons. Group 13 has 3 outermost electrons. Group 14 has 4. Group 15 has 5. Group 16 has 6. Group 17 has 7. And group 18 has 8. So your book points out that the easier way, if you remember this, is to look at the ones decimal place to figure out how many valence electrons it has. Like group 1 has 1, group 2 has 2, group 13, since there's a 3 in the ones place, that one has 3 valence electrons. Group 14 has 4. I can't stand over there, my eyes are watery from being, like, having a LED projector light glaring at me like that, so I'll just stand over here. So group 13 has 3 valence electrons, group 14 has 4, group 15 has 5. And so you can memorize it that way. So make a note that for the main group elements, the number of valence electrons equals the one place of each group. You want to memorize that. You're going to need this over and over and over again, so you might as well memorize it now. Not every single group in the lower sections in groups 3 through 12 follow that rule. So that's the reason why they were given the B letter while the higher ones were given an A letter. That's also another reason for it. So the interposition metals, they don't follow that rule, but you can note that group 1 has 1 valence electron, group 2 has 2 valence electrons, group 13 has 3, and then so on and so on. Alright, your book points out whenever the periodic was first arranged, there were some gaps because scientists had not discovered every single element, but as they put them in this order, they realized, I think we're missing something. And so since they knew that the similar groups had similar functions or similar characteristics, they kind of knew what to look for. I think I skipped over periods. Yeah, each row is called a period. So, like looking at the top, this would be period 1, period 2, period 3. So it starts at the top and goes down. So it's the back and forth line, so left and right. So they say you have period 1, period 2, period 3, period 4, period 5, period 6, period 7. So that's the idea behind it. Let's talk about these a little bit. Alright, I think that's everything for this page. Alright, so the next page for it. That even though this is a man-made tool, it shows a lot of order and design in nature. So your book's just pointing out again that this is an example of how God likes order and design. Now God loves variety as well, but it's the idea of you can find these patterns in nature. And scientists go, it's convenient how this follows a pattern. Now remember, most scientists today believe in the theory of evolution, so that's sad and that's unfortunate. But even they acknowledge that, it is interesting how we have this basically this pattern over and over and over again. And if it evolved, should we really have this pattern? Not really. So it's a good example of showing that someone designed it that way. Alright, a survey of the elements. Now, your book goes through, and if you read this last night, you probably stressed out a little bit thinking, that's a lot of terms and definitions and elements all at once. That's a lot of characteristics. We're going to break it down, we're going to go a little bit slower. Just because I really like it, and I think it's fun, and I get to talk about elements. Alright. So your book points out that there are 3 major groups with your elements. I shouldn't have clicked my slides. I still need it. This is how your book organizes it. If you were in the classroom, we would be using my periodic table. My periodic table is a little bit colored differently, but it's the same basic idea. That you have 3 basic groups based on physical properties. So you have the metals, the semi-metals, and the non-metals. The picture in the book has them as that bluish color as the metals. The pinkish kind of salmon color is the semi-metals. And then the really pale yellow, that's the non-metals. So make a note for that one based on physical properties. Alright, metals, these are typically hard, dense, shiny solids that are good conductors of heat and electricity, and they have high melting point. So something like this is made up of a metal with the idea of it's a good conductor of heat and electricity. It has a high melting point. It's typically dense, shiny. So your book, that's a characteristic of a metal. Mercury is unique. So as a side note, what's the chemical symbol for mercury? Hopefully you know this. You can cheat and look at the chart. Or hopefully you just remember. Hg. Just make a note for mercury for it. Now mercury is unique because it is a liquid at room temperature. Most metals are solid. So your book's pointing out that's kind of unique about it. Most metals are solid at room temperature. Mercury is a liquid. So again, mercury is toxic. Don't eat it. But mercury is a liquid at room temperature. Non-metals are typically poor conductors of electricity and heat. Over half of them are gases and 1 is a liquid. If you have a solid non-metal, they tend to be soft and they have low densities and melting points. So your book points out there's a lot of characteristics with the non-metals where they're not all of them are solid. They can be gases or liquid, and some of them are solid, but not a lot. We'll talk about the reasons why as we get closer to them. Semi-metals or metalloids is another name for them. These are all solids that have properties intermediate between metals and non-metals. So they're semi like a metal, but kind of not. So that's the idea. A semi-metal, it's like a metal, but not really. It doesn't have all the properties that a metal needs. So there's metals, non-metals, and then semi-metals are in between, where they kind of act like a metal and kind of don't. Alright, so we're the different groups. The first group your book talks about is the alkali metals. That's group 1 on the periodic table. So if you flip back a page, you'll notice group 1 has a oh, they don't have it on this chart. Oh, well, make a note for it then. Group 1 has a special name of alkali metals, so make a note for that one. If it were in my classroom, my chart has it labeled. So alkali metals, that's the name for group 1 on the periodic table. Remember, groups is the up and down column. Looking back really quick. So up and down metals, so up and down column, these are all alkali metals, or group 1. As a side note, group 2 are the alkaline earth metals. So I don't have to flip back to the slide. So alkali metals, group 1, alkaline earth metals, group 2. Alright, now I'm going to move on from that. Neat. Alright, so your book's just talking about the different ones for it. So group 1 alkali metals, these all have 1 valence electron, because it's a group 1. So make a note for that one. Many of these metals are important because they only have 1 valence electron, and they're also important because we need these in small amounts. So many metals are important to our bodies in small amounts. Like for example, sodium. This is what pure sodium looks like. You probably see sodium every single day. You probably saw it today, honestly. Alright, what did you eat that has sodium on the inside? Like sodium chloride. What is that? So that is drawn as NaCl. So what is it? Do you recognize it? Table salt. This is regular, just table salt. So you eat a little bit of sodium every single day. Now sodium chloride is safe because the sodium is bonded to the chlorine, but you eat a little bit of sodium every single day. You need it. So sodium is found in table salt. Potassium is another one. So potassium, you also need to know. You probably think of one major fruit. Whenever you think of potassium, what fruit do we associate potassium with? Bananas. So that's probably the one you said. There's a couple of other fruits and vegetables you can get potassium from, but bananas is most well known from it. Here's what sodium looks like. Whoops, wrong direction. Here's what potassium looks like. So make a note of those two for it. You need them for your muscle contractions. That's one reason why if you get muscle cramps, typically we say it's because you don't have enough potassium. In America, you get plenty of sodium. There's plenty of salt in American food, so you don't have to worry about eating extra salt. But in a lot of cases, since sodium and potassium work together with your muscle contractions, if you're getting muscle cramps, you probably don't have enough sodium. Most of your parents might tell you to go eat bananas or something else to get potassium, so that way it helps out with your muscle contractions for it. Your book points out elemental sodium is put in some street lamps, giving it a yellow color. Sometimes street lights, whenever they start to glow kind of a yellowish color, it's because of the sodium on the inside. They don't really use it like that a lot today though. Sodium hydroxide is also called lye or caustic soda. It's a corrosive metal. Alkaline metals, they combine very easily with other metals though because they only have that 1 valence electron. They want to get rid of it because remember for the octet rule, you either want 8 valence electrons or none at all. So they go, okay, I have 1. Which is easier, lose 1 or gain 7? The elements decide, lose 1, and so they will throw off that 1 valence electron. And that's why whenever you have sodium chloride like this, sodium is giving away its 1 electron to chlorine. So it's trying to get rid of that valence electron because it doesn't want it anymore. Now you'll notice hydrogen is not included in the alkali metals. Look at the table on page 131 back on your chart. You'll notice it's that yellowish color like the other non-metals. That's because even though it's in group 1, it has that 1 proton and it has that 1 valence electron, it doesn't act like a metal. So that's how come it's over on that table side, but they color it like a non-metal because they're saying, hey, it's not considered a metal. It has 1 proton and typically 1 electron, but we're not counting it as a metal. So hydrogen is not included in the alkaline metals because it has a very different properties. Alright, so that's what you need to know about the alkaline metals, so sodium and potassium. Alright, group 2, alkaline, or wrong direction. Group 2. These are the alkaline earth metals. Make a note for them. If they're in group 2, how many valence electrons do they have? 2. Good job. So the alkaline earth metals are harder, denser, and less reactive than the alkali metals, but they're still softer and less dense than most metals. They are also reactive though, because keep in mind, which is easier, lose 2 electrons or gain 6? Lose 2. So they will still react to get rid of those valence electrons because they either want 8 or none at all. Alright, so your book points out all these metals are silver colored except for beryllium. So this one is pronounced beryllium on the side. This is what beryllium looks like, or one picture for it. So this one, your book points out, is highly toxic, but it's prized for its strength and light weight. So let's see. Awesome. I got confused because magnesium was right after it. So this is a picture of beryllium. Beryllium is also in a semi-precious stone. I think we talked about this last year. If you were in Earth and Space Science, and we talked about what semi-precious stone beryllium's in. Do you remember? Right, it's an emerald. So this is a compound of beryllium. There's other things in it, but beryllium makes up emerald. So it makes up that pretty green semi-precious stone. Alright, magnesium, this is another one. So this one is used extensively in airplanes and race cars. Powdered magnesium, it burns a brilliant white flame, and so it's used in signal flares and disposable flash bulbs. So magnesium is what it normally looks like if you get pure magnesium. You can also use it in several different things as well. So it's prized for its strength and weight as well for it. And then if you light it on fire, it burns a brilliant white color. So sometimes you'll see it as fire starter kits, that it'll be used in order to cause a really hot fire. So you use it in some cases in these fire starter kits as well for it. So your book should point out some of the different uses for it. Alright, calcium is the next major one. Now what do you use calcium for? Right, your bones and teeth. So we associate calcium with bones and teeth, and you need it. And here's what pure calcium looks like. So again, silvery color. All these metals are kind of similar right now, so I know it's not that exciting to see them. But you need calcium. It's the most abundant alkaline earth metal, and you use it on the inside of your body for your bones and teeth. You need a little bit of calcium. Actually, you need a lot of calcium every single day. So it'll help out with your bones and teeth and make your bones strong on the inside. What happens if you don't eat enough calcium? Well, your body uses calcium besides just your bones and your teeth. Your body actually uses it in your muscles and in your blood as well. So if you don't get enough calcium, your body knows you have calcium stored on the inside of your bones, so it'll literally take it out of your bones and start pulling basically and making holes in your bones if you don't get enough calcium. So we call that osteoporosis in some cases. So that's probably the reason as to how come you want to make sure you drink milk every single day and then get vitamin D. But you want to make sure you're drinking milk every single day. So that way, as you're growing as a young teenager, well, some of you, you're getting a little bit older now, but you're still growing. And so because of that, you want to make sure you're drinking calcium every single day. Alright, so I believe I'm just about out of time. This is a good stopping point with calcium, finishing up that section for it. So I'll go ahead and stop there because it's a quiz. It'll probably take you a little bit longer. So we'll go ahead and we'll stop here for it. Alright, your homework for tonight. Read pages 136 through 140, 136 through 140. Answer on page 136. Questions 1, 3, and 5, and on page 140, questions 1 through 6. I know it's a lot, so it's okay though. So you're going to read pages 136 to 140, 136 to 140. Answer on page 136, questions 1, 3, and 5, and on page 140, questions 1 through 6. Don't forget, the final draft of your background paper is due Monday. So I need both copies. The copy without your name on the title page for the judges in the spring, and then the copy with your name on the title page for me to grade. So I need both copies for it. So one of them, they should both be the exact same. The only difference is that title page. Title page for the judges in the spring, for the academic fair, should not have your name anywhere on it. The one for me to grade should have your name on the title page. Be sure to have your parents email me if you have any questions about your background paper. And I hope you have a good day, and I will hope you have a great weekend.